Alright, hello everybody, and today we're going to be deriving the arc length formula for any function on a continuous interval. So I've already drawn up a little picture here. So we have some function f of x here, represented on this y-axis. So we want to find the arc length, say from this point, we'll call it A, to, I don't know, this point B. There we go. So we want to find this arc length here, and I want to relate this back to finding the area under the curve. So we're going to be using integration for this, obviously. So let's see, we have another function here. We want to find the area from A to B. So we want to find this area here, and how we did this is we took some small slither here. So we wanted to find an area, and we just split it up into very small areas. So I'm just coloring this little area in bold. So we took these little areas and we made them very, very, very small, and we added them up using the integral. And if we look back over here, we can kind of relate back to this. If we want to find this arc length, seeing how it's always changing, we can consider very small intervals. So say from here to here, we can find, say, this little length here. And if we have some expression for that, then we can just add all of them up using an integral. And we want this little length here to be in terms of x, because see, our boundaries here are in terms of x. Just as we had for finding an area under a curve, we had integral of some function times dx. This f of x times dx is exactly each of these little slithers here. So we have the height being f of x and our little width being dx. So this is in terms of x and our bounds are in terms of x. So this is good. So we want to find some kinds of expression for this little length here in terms of x. So I'm just going to make this a little bit bigger, exaggerate all my work here out for you on this diagram. So let's see, if we want to find the length from, say, this point to this point, how can we do it? Well, we can consider a change in the x value and a change in the y value. And if we connect these 2 points here, we get a triangle. So let's call this hypotenuse here ds, and the idea is similar to integration. We want to make everything here approach 0. So the smaller this becomes, the more accurate our approximation is. So if this is ds, well, if this length approaches 0, this will become dx, and this height here will become dy. So we want to find ds in terms of dx. So let's see, I'm just going to draw up another picture here. So this is the triangle we're looking at here. So we have our ds here and dx down here, and we have a dy here. I'm just going to rub this picture out because we don't really need it anymore. So this is a right angle triangle. So how can we find ds in terms of dx? Well, we can first of all relate all the sides. So we have, let's see, we have dx squared plus dy squared. That's exactly our ds squared. So we want to isolate this ds here. So let's just take the square root on both sides. So we have our ds is equal to the square root of dx squared plus dy squared. And the idea now is to somehow get a factor of dx out here so we can actually integrate this thing. So I hope you agree with me that the ds is also equal to, so we have dx squared in here, and I'm going to modify this dy a bit. I'm going to multiply it by dx on dx, and then attach a dy there, all squared. So this is just kind of like saying 1 times dy, so nothing changes. So now, since this is a fraction, we can kind of rearrange it a bit as we can with other fractions. So this is a dx squared, And then now, if we move this dy up to here, notice that we have a dy on dx times dx. And this is a derivative in terms of x. So now we can kind of expand this power, this square here. So we have dy and dx squared times dx squared. And this is really good because now we have a common factor of dx that we can factor out. So notice that this is a dx squared, and when we factor it out, we can cancel it with the square root. So in the end, we have ds is square root. Now I'm factoring this dx squared out, so we have 1 plus, and I'm going to rewrite this dy and dx as f prime of x. So we have f prime of x squared, and then we factored out this dx squared, but because we have the square root, it just turns back into a dx. So now we have an expression in terms of x for each of these little intervals here. So now we can use an integral to add all of these up, and because they're respect to x, we can integrate them across an interval on our x-axis. So let's see. I'm just going to rub out this picture here, we don't need it anymore. So in the end, if we want to find the arc length across some interval on the x-axis, all we do is we integrate. And now remember, this part here, this is just representing each of those little lengths I was showing you. So if we integrate all of these little lengths, so 1 plus f prime of x squared times dx across some continuous interval a to b. This is exactly the formula that we use to find the arc length of a function. So there we go. So now I'm just gonna get into a quick example here, just to show you that it works and everything. So let's just consider a function. An easy function to do is a semicircle. So this is the function I'm talking about. So we have a semicircle. This function is square root of 1 minus x squared. So this is y equals to that. So we want to find the arc length from -1 to 1. And of course you can just use your circumference formula for a circle to find it. So this would just be exactly pi. But we want to use our arc length formula here. So let's just throw all of this information into here. So we know our bounds are -1 and 1, and our function is, and this should be equal, our function is square root of 1 minus x squared. So first of all, we want to find the derivative of that thing. So if we differentiate this, what we get is -x on square root of 1 minus x squared. So this is, you can say, f prime of x. Okay, and in this formula here we have f prime of x but squared, so we can just square this thing. So f prime of x squared is equal to x squared times 1 minus x squared. So now we can plug this information into here. So we have the integral, and our bounds are -1 and 1, and we have big square root of 1 plus, and this f prime of x squared is this thing we found right here. So we have x squared over 1 minus x squared, and then we have a dx hanging off the ends here. Alright, so now we want to kind of combine this a bit to make things neater. So I hope you agree with me that this is just the integral from -1 to 1 of the square root of, I'm going to change this one to a 1 minus x squared over 1 minus x squared. So this is just a 1 here, and we're going to add that with x squared over 1 minus x squared. And it's pretty obvious I did that so we can have a common denominator here. So let's just rub all this stuff out. So now we have the integral from -1 to 1, and I'm going to add these two together. So -x squared and x squared will cancel. So just going to have a big square root of 1 over 1 minus x squared dx, and we can square root of 1 is just 1, then we can just square it at the bottom. So this is the integral from -1 to 1, 1 over square root of 1 minus x squared dx. And if you know this integral, this is just the arc sine of x. So now we have arc sine of x, and we want to evaluate that from -1 to 1. So we'll just plug in the values. So sine, inverse sine of 1, that's just pi on 2. So you have pi on 2, subtract the lower bounds, sine inverse of -1, that's negative pi on 2. Negative is positive. So in the end we have pi on 2 plus pi on 2, and that is pi as we were expecting. So yeah, that's it. Hope you guys enjoyed this video, and I will see you guys next time.